Well, then I will give a slow introduction to let people filter in. I've known Mark since 1990-ish back in Seattle, and we have had many adventures. And all of those adventures have been based around science, actually. It's been great. Like, we use scientific studies, and we use consulting opportunities as excuses to go find good restaurants and bars in different places in the United States. Yeah, and it's been a great, fun journey so far. Not over. Mark has a BA from San Diego back in '90, and a master's in forestry back at the University of Washington. That's where I met him. We were both studying urban aquatic systems. And a PhD in hydro, and then we worked together at a consulting company for a few years, having some adventures. And then he went on to go get a PhD at Davis in hydrology, and now he is a professor of geology at the University of South Florida and the director of geosciences. I had to read all these things. I don't know much about them. He's the director of the School of Geosciences there, associate editor of Wetland and Watershed Hydrology and the Journal for American Water Resources Association, and also he's president of Show Environmental, which is a small consulting firm. His research is hydrologic connectivity from ridges to reefs, especially from hill slopes, wetlands, and headwater streams, and the role of these hydrologic processes in governing structure and function of ecosystems. But also, the roles of how these science plays to informing water-related law, policy, and decision making. He's been very active in waters of the U.S. discussion. He was on the Science Advisory Board for EPA, and he had ongoing scientific justification for the underlying federal definition of waters of the U.S. for the Clean Water Act with the Obama administration. And since then, has been kicked out of all that and got fired. And now he's actively responding to the Trump administration's definitions of the waters of the U.S. and has been played some central roles in two big cases in the Supreme Court under what defines those parameters. So his talk today is going to touch on some/all of that, and I'm looking forward to it.
And probably the proudest thing of that whole introduction is that I was fired by the Trump administration from the Science Advisory Board. Probably when that should go on my epitaph. Feel pretty good about that. I'm not really going to talk about waters of the U.S. though today. I'm going to talk about groundwater subsidies, the Salmonid streams. I said it's a decade. It's actually more like 13 or 14 years we've been working up here. And so there's a lot I got to cover in a short amount of time. So I'll go a little bit fast at times. If I skip over something, hold me back, and I'll answer some questions if I can. And it's only going to be about half science. The other half's going to be what I call outcomes here, by which I mean how we have engaged their stakeholders to change the way they think about and interact with and manage their own natural resources. And I kind of feel like that's probably the more important things. How do we move the needle in the way people are behaving? So this is a story centrally, oh, hold on, I'm gonna use this thing. Story centrally about not knowing how to use technology. Did it freeze? I gotta wake it up. That was what you're telling me, Madison? Yeah. There we go. So it's centrally the four-letter word that starts with F in Alaska. That's fish. Big parts of obviously ecosystems, keystone species to the ecosystems. Probably more importantly, from an Alaskan standpoint, is big parts of the economy, big sport fishing economy, massive commercial fishing economy. I heard a number from Bill yesterday, $13 billion of annual economic activity associated with fishing in Alaska alone. It's about 0.5% of the whole GDP of the United States. Maybe even more importantly, from a day-to-day perspective, is it's almost a cultural touchstone for average Alaskans who all have subsistence rights. They can literally like take a big net, go down to the ocean and just net salmon and fill up their freezers, and all of them do. Tony's probably done that at some point in his life. And so it was in that context we started working down in the lower Kenai Peninsula, the Kenai lowlands. This is the non-glaciated portion of South Central Alaska. When we first started this, about 2006, and we were simply doing some of the first electrofishing in the headwater settings. There just wasn't known if juvenile salmon's used or overwintered in these settings. Some of these are tiny, a couple tens of centimeters wide, maybe a couple centimeters in depth, and you literally couldn't electrofish one without pulling up a whole bunch of juvenile salmonids, kilometers away from the nearest spawning habitats. And so every place that you see a dot is a place that we or part of our team electrofished, and all the lines tying them together are all the streams that are now mapped as being used by juvenile salmonids. So it massively changed the way they started thinking about this resource. They're everywhere. Well, as we were walking around, the other thing we noticed is that it's the leakiest dam landscape I've ever worked in. Like, you literally can't throw a pencil without it landing in a seep or a spring. Just virtually everywhere you go. It's super hard to miss them. And so we started thinking about that there must be an important role for groundwater in connecting hill slopes to headwater streams and controlling the structure and function of those streams. So we started thinking about you got a headwater basin, and you've got groundwater flows, which I've represented here with that dotted line, and those groundwater might move underneath a alder patch, which fixes nitrogen from the atmosphere, makes it more available at the hill slope scale, and then all of that water might go down, interact with streamside wetlands, and all of that then might make some sort of a cocktail that results in the hot spots, or maybe even the hot moments downstream that result in salmonid production. That's sort of a big fluffy way of talking about all the many hypotheses that we've concocted along the way. So that's the conceptual framework that we started with. Before I go any further, I have to talk about what I mean by groundwater. And there's two flavors here. These are real places. Headwaters of the South Fork Anchor River, and this is the main stem of the South Fork Anchor River down there. A lot of times this is just hill slope groundwater. So it's annual snowmelt, annual rainfall. It infiltrates into the shallow subsurface, maybe the upper half meter, and begins moving laterally down. And if there's little hollows, maybe there's discharge on the hill slope. Otherwise, a lot of this water just diffuse discharges to the stream itself. That's something that happens on the scale of days to months. So whatever happened this year matters. If it was a wet year or a dry year, if it's rained recently or not, would affect those processes. The other one is sort of longer scales. This is this is actually a real place here. It's a must dig there. You got deep recharge down into these thin aquifers. One here is sand. Let's see, sand and gravel. That one's sand and coal. And that water gets down into these thin aquifers, which might be 2 meters in thickness, 3 meters in thickness, not super productive. Then it moves laterally and discharges at seeps and springs where those aquifers outcrop at the hill slope. Two kind of different processes. This one operating on days to months, the other maybe on years to decades. Doesn't really care if it was a big wet year or dry year in one case, and it does in the other. So we started thinking of this in simple terms first, and that was stream flow. There's a whole bunch of stuff here that doesn't matter. What really matters is this down here. We're just doing sort of simple mass balance mixing models. How much water in the stream began as water underground? And there's a bunch of stuff in here about geomorphic setting, which turned out didn't matter. One of the many hypotheses that didn't work out. Then I was standing, here's the spring results. About 40% groundwater in the stream flow in summer, which would be sort of late July before the Alaska high breaks down and it starts to rain, soon misses snow, maybe 60%. So let's just say half. Let's just say half the stream flow in summertime came out of the ground originally. In the wintertime, it's more like 100%, right? It gets pretty cold, as we'll see here in a moment. And so any water, especially in the smaller streams, is going to freeze unless there's some source of warmer water that's coming in. That warmer water, which we'll see here in a moment, in groundwater. In fact, we're going to see it now. So we put in a whole bunch of wells in adjacent to these headwater streams. So here's this little headwater stream. I'm standing on the other bank. It's that small. You can see the bottom. It's pretty shallow. It's one of my students, Jason Molino. He's got a shallow well he's installed up on the hill slope a little ways. And then we've done this all over the place. There's just a typical plot where you've got temperature here, date there. That's a whole year. The dashed line is the air temperature. The black solid line is the groundwater temperature, and the gray solid line is the surface water temperature. And just by way of orienting you, that's 0. Okay. So as you might expect, it gets really cold in winter. In the winter time, it's really hot in the summertime. That's that. But the stream and groundwater don't seem to care that much. They're modulating it. Right. They have very similar shapes to those lines. Most important thing being that surface water never drops to 0. So it stays liquid all winter. And in this case, it's a function of this groundwater discharge. Now, this isn't continuous, and we'll come back. I think I should talk about that next. So when groundwater comes out of the ground, stops being groundwater, starts being surface water, right? So earlier I said, half the stream flow is groundwater. I mean, half the stream flow started as groundwater, but as soon as it came out of the ground, it became surface water. It starts equilibrating, in this case, with the atmosphere, which means it's going to get colder in the summer or winter, warmer in the summer. So we did some work looking at just modeling that. And we modeled it 2 ways, and we did it in all sorts of different reaches. And again, this is just an exemplar. So here's temperature here. Oops, hold on. Here's temperature here on the y-axis, and this is distance here in meters. And so we broke this, I think, into 250-meter segments. The solid black circle run is we inject the same amount of groundwater in each reach. So we measure groundwater discharge on a number of reaches, just come up with a value we want to run. We got the temperature of that. This is just an energy balance approach. And so if you inject groundwater of the same temperature at every reach, it keeps the temperature relatively constant. In this case, it was 8 degrees Celsius coming into the upper reach. The other model run is the one with the open squares. That's where we just inject groundwater in the first reach, and then we stop. No more injection of groundwater. And you can see this immediate deviation as that water that was injected here begins to equilibrate, and the temperatures increase in the downstream direction. Now, there's all kinds of things that go into this, right? What was the temperature of the water coming in? How much water was coming in? How much groundwater was coming in? What's the temperature of that? What's the shade and aspect? And how hot was it on these days, and so on and so forth. So any run you do looks different, which is why I'm just saying this is an exemplar. But they all have one thing in common, which is that they have some length scale over which there's some temperature change. The important thing, though, to keep in mind here is that it's immediate, right? As soon as we stop injecting groundwater, it starts to equilibrate. So this is a local scale effect, at least from a temperature standpoint. So what does this all mean? Well, it's sort of, you've got summer on the left and winter on the right. This is the groundwater discharge coming out of spring. The toe of the slope just sort of just back on that terrace there, cascading in and flows from left to right. It's kind of warm, it's July, and water coming in is 14 degrees Celsius right there at that cascade pool, it's 6. Well, okay, it's kind of an interesting, probably not that big a deal because both of those are well within the range of the normal metabolism for these salmonids. Their brains aren't cooking until you get quite a bit warmer than that. So maybe there's some summer effect. Biggest effect though might be over here. Right? I'm standing in the middle of the river, which is apparently 0 degrees Celsius because I'm not cascading through it. But in the background, there's a little spring and there's some slushy water that's 1 degree Celsius. I'm about to throw those traps in there, these minnow traps. They're going to fill up with juvenile salmonids overnight. And if we lavage them, out is going to come a whole bunch of food. So they're eating and metabolizing. Out's going to come, oddly enough, earthworms, which I still haven't figured out quite how that's working, but that's what they're eating in the wintertime. And we've got all kinds of evidence to suggest they're not just metabolizing, they're growing. So these are overwintering juvenile salmonids that are going into the winter like this and coming out like that. And they're only doing it in these sort of small microsites where the water is staying liquid all winter. The story gets more complicated as you start thinking about nutrient dynamics. So this is that lower Kenai Peninsula here. The dark gray are places where we've mapped alder patches. So again, alder, if you're not aware, have a symbiotic relationship with bacteria that live in nodules in their roots. They can pull nitrogen out of the atmosphere, make it a mineral form, which could be uptaken by the alder. which then when the alder drops leaves or decays roots or otherwise, that is then mineralized and it's available at the hill slope scale. So on the left here, you see dissolved inorganic nitrogen on the y-axis by percent alder cover on the x-axis. If there's a lot of alder in the basin, then there's a lot of nitrogen, dissolved inorganic nitrogen in the stream. If there's not much alder in the basin, then there isn't. And it's a linear relationship here. Pretty good one too, right? Well, that's interesting, but it's probably not that surprising. I mean, we would have, and in fact did, predict that nitrogen concentrations in the stream would be some function of alder cover in the catchment. Over on the right, things get a little more interesting still. So this is still percent cover of alder on the x-axis. These are log scales in this case. On the y-axis is end fixation rate of the stream biota themselves, right? So if there's a lot of alder in the watershed, the stream biota themselves aren't fixing much nitrogen. But if there isn't a lot of alder in the watershed, and therefore there isn't a lot of nitrogen in the stream, then it selects for a whole different stream biota, which is better enabled to fix atmospheric nitrogen. So this was interesting and a little bit surprising. The streams themselves are restructuring relative to the nitrogen concentrations, which are a function of the alder cover and the groundwater that's connecting those alder to the streams themselves. That's not the whole story though. So we started looking at primary productivity adjacent to the streams, and the wetlands adjacent to the streams, and seeing if there was some relationship between alder fixed nitrogen moving through the groundwater and affecting the primary productivity of those streamside wetlands. And that's what this work is here. My student Mike Callahan, also Benny Wiggum from Smithsonian. It's a lot here, but let me just focus you on a couple things right here. First of all, let me tell you these flow paths. So you can have a flow path where there's alder right up next to the stream, or right up next to the streamside wetland, or you can have a flow path where there's alder way up the hill slope, but still that flow path ends up in that streamside wetland. Or you can have a flow path where there's no alder at all. I've circled here the biomass of Calamagrostis canadensis, which comprises about 85, maybe 95% of the biomass in the streamside wetlands themselves. That's sort of universal up here. And this is the control. So you can see that whether the alder is near or far, it's about the same. Okay, about the same above ground biomass, by the way. It's an important caveat. But when there's no alder at all, there's about 60% of that biomass. So the streamside wetlands without the alder cover on their hill slope have less above ground biomass. If you spike them all with nitrogen, so we basically fertilize all these wetlands, then look at the green circles now. There's hardly any effect when there's alder near. There's a larger effect when the alder's far away. There's this massive effect when there was no alder at all. And these become not statistically significantly different from one another. So in other words, this is clearly a nitrogen effect, right? I mean, if I add nitrogen, they all are just as happy, which wasn't the case before the nitrogen was spiked itself. So at the bottom, we can sort of simplify that. If we think of the biomass ratio as the fertilized biomass divided by the pre-fertilized biomass, and since these two actually aren't statistically significantly different from one another, alder near and alder far didn't seem to make that much of a difference, let's lump them into an alder flow path category and then take this one down, and that's the no alder flow path category. One would be there's no effect at all. So you see this slight effect. If there had been alder on the flow path, there's a little bit of an effect. If there was no alder, there's this massive effect. It's more than a double. Keeps going. Ignore this for the time being. Let's just focus here. These are the streamside wetlands, and this is the Calamagrostis canadensis. That's the stuff that has just died, is about to drop into the stream itself. And it turns out when it does end up in the stream, the breakdown rate, in this case degree days, is a function of the dissolved inorganic nitrogen concentration in the stream. So again, if there's a lot of alder in the watershed, there's a lot of nitrogen in the stream, and the Calamagrostis canadensis litter breaks down more quickly than the opposite case. And they can do this apparently. I don't know a lot about bugs, maybe somebody here does, but apparently they can uptake, like the shredders can uptake nitrogen through their gills. That's what Becky Schachtel said in this paper anyway. And so they're more efficient, right? They can, you know, they have that as a source of nitrogen, and apparently affects the breakdown rate. We also looked at the energetics related to this dynamic. There's a lot going on here. There's actually multiple reaches. I've just selected one reach. I hope you don't ask me a lot of questions about this because I don't know it that well. But suffice to say, these are plots of delta N15 by delta carbon 13 or delta H2. A lot going on here, but let me just simplify it to this. Those right there are the domains of the autochthonous producers and the low-level autochthonous consumers. So these are the guys that are in the stream producing and the original consumers. That's the domain of the allochthonous producers. In other words, that Calligrossus canadensis, and the allochthonous low-level consumers. Now we would expect fish on both of these axes, if they're consuming one source or the other, to plot directly vertically up along the delta N15 axis, and that's what you see here, the red are the fish. So these guys are getting their bulk of their energy along this path here from the allochthonous material. So the fact that you've got high productivity in the stream side wetlands associated with these alder flow paths, it's dropping into the stream, and that stuff can be shredded and turned into shredder bugs, which then can be eaten by juvenile salmonids, starts tying this whole thing together. So here's the full conceptual model, right? You've got groundwater flowing from a hill slope down into a stream. Sometimes it passes underneath alder, where those nitrogen-fixing nodules on the roots. Nitrogen-rich groundwater is the result, which starts moving downstream to where there are stream-side wetlands. It's not really looks like this. It's either a fen or it's a mineral soil wetland, but one or the other. There's typically a stream-side wetland where that nitrogen-rich groundwater produces carbon, which then serves as a food source there. So this water comes out, modulates temperature, modulates dissolved inorganic nitrogen concentrations in the stream, plus helps the production of stream-side vegetation, which ends up in the stream, chewed up by the shredders, uptaken by the fish. Yeah.
Can you just highlight the autochthonous and allochthonous in this cross section?
So the autochthonous stuff would be this stuff down here, the alphus, right? It's like little, or submerged aquatic vegetation, or mostly algae, right? And then it's the bugs that are cruising around down there that live their whole lives down there. The allochthonous stuff is this stuff here, right? So it's mostly Calligrossus canadensis and the critters that are living in that stream bank vegetation, all of which are falling into the stream itself and then becoming the food sources. That's the end of science. If you don't want to hear about science, you might want to leave, because I want to talk about something else now. And that was what I warned you about. I want to talk about the outcomes and how we've affected change up there. To do this, I started thinking about this last fall, and I read the Chronicle of Higher Education like daily, well, 5 days a week. And I came upon this article, rather unapologetic title, Can Universities Save the World? A new movement is underway to find out. And then even more recently, another one came out. Max Weber invented the crisis of the humanities. More than 100 years old, his landmark essay is more relevant than ever. Both of these articles dealt with this same guy, Max Weber, who has a disproportionate influence on your life, whether you know it or not. So Max Weber, interestingly enough, he was an academic, but he was sort of a failed academic. By the time he writes this essay that I'm going to talk about, he's out of academia. He's sort of had an emotional breakdown for reasons that'll become clear in a moment. This is 1917, Germany, right? What's going on? World War I. And if you recall your World War I history, 1914 it starts, the Germans have the Schlieffen Plan to win the war within weeks. And when they don't, they're almost definitely doomed to lose. By late 1914, early 1915, that's almost the only possible outcome. So they embark on a war of attrition. They're just going to wear us down. They're going to kill so many people and ruin so many lives that they're hoping that the other side gives up before their side does. That's the plan by early 1915. And to do that, because they're a smaller country, they're landlocked, they're fighting wars on two fronts. To do that, you've got to conscript the entire society. First ones you go for are the scientists. So people like you and me get conscripted into the state. We're the ones that are going to help invent better ways to kill more people more quickly. Bombs, gas, the whole thing. But we're also important because we're the ones that can convince the students to leave the university and jump in a trench and become the fodder for the other side, right? So this is like how it works. And Max Weber's like, what the heck happened? Like, I had this great life as an academic, and now I'm part of the state. And so he has a nervous breakdown. He backs out. He aligns himself with a movement of youth who are saying, this is BS. Like, we're not into this at all. And there's some pushback. And he's joined that movement. In 1917, he writes an essay and gives this talk. Science is vocation. There's a translation problem here. That could maybe mean academic more generally. So he's writing this paper, and here's a great quote out of it. If a scientist feels called upon to intervene in the struggles of worldviews and party opinions, he may do so outside of the marketplace and the press and meetings in association wherever he wishes. The key here is outside. So there's personal Mark Raines, and I go to coffee shops, and, complain about things, and I go to my city council and complain about things, and I can vote. But the professional Mark Raines has to be completely separate. And that's the only way that professional Mark Raines can reach true enlightenment. In fact, I shouldn't even be talking to you guys, because you're not, how many geologists? I'm only supposed to talk to you according to this essay, right? It was like really defining our domain. I should know so much about one small topic that I have no friends and colleagues. That's the goal, right? Well, this happens at a really important time. So this is 1917, this comes out. 1905, Pancho Villa and a bunch of banditos literally ride horses across from Mexico into New Mexico. And they like shoot up a town with handguns. They burn the town down, all these people die, and they ride back. The United States government's like, oh, hey, that sucks. So let's get General John Pershing, a 5,000-man army. And they go across into northern New Mexico to catch Pancho Villa. Planes crash, and their cars break down, and they get lost, and they never find Pancho Villa. They come back totally defeated. We're literally like a backwater frontier country, and everybody thinks it. World War I comes around, we're not involved. First of all, it has nothing to do with us. Second of all, we don't even know how, or we'll have the resources to do it. We didn't even catch Pancho Villa. We're going to defeat, the Third Reich. Well, so what do? We stay out and we profiteer. We actually profiteer from both sides. More so from the Allies. It's the largest transfer of wealth in human history. Center of banking in the world goes from London to New York City. 1918 rolls around. We come in, we sweep up the end, and we announce ourselves in 1919 as a superpower. Whole world changes for the United States. And this is now a plot of number of colleges and universities by year. That's 1917. So all these universities get built in this early version of a viral essay, Weber 1917. We build our universities around this concept. So we all know what this looks like, right? It's the ivory tower. So here we are in the ivory tower. We're saying smart stuff. It's apparently math stuff. Not even our colleagues in history can understand it. And there's all these people, like, as far as the eye can see. And they're like, hey, why won't the scientists talk to us? Well, we won't, because that's not our job, right? That's not how we're built. I got tenured and promoted to full professor because I got grants, I wrote papers, I went to conferences, and we all do the same thing. Very few of us. Are there any extension agents in here? I know you're in land grant school. None, right? So that's a different job. But the rest of us don't get rewarded for that. We get rewarded for the traditional academic pursuits. So we're not built to talk to the people. Sometimes we do, but if we do so, it's on our own accord. But go back to those articles. There's a rethinking of what the university's role, right? Can the university save the world was really about reorienting our work towards community engagement. So my university, University of South Florida, has an office of community engagement and partnerships. And whether you knew it or not, you have one too. Most of us do now. And these are groups on campus that are created to sort of help us engage in community engaged scholarship. Well, University of South Florida, Montana State are hardly the vanguards here, right? This is happening everywhere. So there's three major organizations that are multi-institution organizations. This one here has 1,100 members. This one more than 13. This one has 40, but some big hitters there. My university's a member of those. Yours is a member of all three, right? So it's a not so subtle way of telling us we're supposed to do this. And we could probably come back and have a long conversation about maybe they ought to reward us for it. Maybe we'll save that for afterwards as we talk, maybe over beer later this afternoon. Colombo, I guess, or whatever it is. But we're certainly being told to do it. So how do you do it, right? So we've conceptualized this. This is how we normally work, right? We go get information, which is like data, and we create knowledge, which are our papers. And then we would normally loop back here and get more information to create more, maybe over here. And the expectation is there's a bunch of end users and they'll take care of it themselves, right? So what we've done in this project in Alaska, finally back to Alaska, from Poncho Villa to Alaska, is we've brought the end user in here. They're in the knowledge, we co-produce that knowledge with them. They're full partners in our projects. And so that we can help them take our knowledge to create new intelligence, modify behavior, and get outcomes. And then we're continuing to talk to them so that we can, they evaluate and revise their questions and needs. That feeds back into us, which informs what's the next thing we do. So it's a full co-production of knowledge. So that means you got to start engaging people on levels that work for them. So we've all said this, right? If they only understood, they make the right decision, right? It's all about education. People need more education, and then they'll do X, Y, or Z. That's called the deficit model, and there's a ton of research that tells us it's totally wrong. Like my favorite example is a climate change paper where they took 100 bits of information, they mirrored the scientific consensus, and so like 97 was information that supported climate change, and 3 pieces didn't. And the people who were predisposed to disbelieve climate science didn't get convinced by the 97, they got really good at making their arguments on the 3, right? It's not that they didn't have the information, it's that they didn't trust where it came from. So in order to get there, you actually have to build community credibility. Expertise is part of that, right? You have to be seen as an expert. But there's like, we've all grown up with movies of evil geniuses who didn't have our best intentions at heart, right? So you have to also build that as trustworthiness, which is a function of intent. If I'm seen by my stakeholders that have good intentions, especially if my intentions align with theirs, then they can establish a feeling of warmth to me. Hey, he's not only credible, I have good feelings toward him. I want to hear what he has to say, and I'm inclined to believe it. So you can take these things and ask people about different jobs and where do they plot them on an axis or a plot of warmth by competence. So where are we? We actually don't do too badly. We're way over here on the competence side. Like we're professors and researchers and scientists. That's pretty good. At least they see us as competent. And we're actually not so bad on the warmth axis. I mean, at least we're not lawyers. Right? But nor are we doctors or nurses or teachers or childcare workers or even farmers. Well, those are our stakeholders, right? So our stakeholders say, yeah, they're competent, but they're not nearly as warm as we are. So how do we move up that warmth axis? How do we get up here and nail both the competency and warmth axis? Well, I think you can learn something from lessons we've learned as we've tried to convey natural hazards risk to people. And so here's a plot here. I've sort of replotted it. These are the factors in successful communication of natural hazard risk. There's our expertise, our competence. There's our trustworthiness. That's that warmth. They're still there, right? There's a whole bunch of other little things people will say matter. And look what half of it is. It's listening, caring, appearing empathetic or compassionate. Half of it is just that. Well, here's the scary thing. You have about 30 seconds to establish this. Some estimates as low as 9. I mean, we're really good at this. Like, is Scott going to eat me? Well, I better figure that out really quickly, right? So we're really, evolutionarily tuned into making some quick decisions about the people and critters we encounter. So here's one. And somebody's old saying, you never get a second chance to make a first impression. Turns out you hardly get a first chance. Like that's it, man. 30 seconds. And so that made me think. I started remembering one of these internet memes. You probably have all seen it. The theologian Dean Augsburger. This being heard is so close to being loved, but for the average person, they're almost indistinguishable. So your stakeholder just wants to know that you're listening. That means if you write a paper, you go to a conference, or you stand up at a public meeting and you talk at them, That's not going to do it, right? That's not the way to engage them. You have to engage them in a way where they feel valued and their opinions feel valued. Hence, this idea of co-producing the knowledge with our stakeholders. So that means we undertake sort of the laborious and professionally unrewarding, though personally rewarding, efforts of actually engaging our stakeholders at their times and in their places of choosing. Right? So here's the borough, which is the equivalent of a county. Right? So there's Marcus, he's the lead planner. There's Bruce, he's in charge of the permitting for aggregate mining, which is a big deal there. We're standing in the field. This is, by the way, that picture is probably taken by Bill. This one too, probably taken by Bill. Here we are talking with the Kenai Heritage Land Trust about a blue carbon project. This is the Homer Soil and Water Conservation District. There's Bill working vertical. And even to the extent that we hold webinars, here we are sitting in our web conference room in Florida, and this is sort of a multi-stakeholder webinar. I've got feds, state, locals, everybody involved. And here in this case, we're showing some of our work, but we're listening just as equally to their work and their own, sometimes folk knowledge. Like they still divine up here, like water witching, like that's a thing people do. Stuff like, okay, well, go talk to those guys. Turns out they know a lot about how to find water. And it's even down to stuff like this. So there I am, there's my co-PI in White Sky, our longtime friend Karen Noyes, now Karen DiCino. She married Bob DiCino. They said, hey, come on over. You got to meet Bob and get to know him a little better. We're having moose meatballs. And I say, oh, you work for Fish and Game, right? You guys are our stakeholders. And he says, oh, who? And I tell him who. And he says, no, I don't know those guys. I had never even heard of them. I'm like, how's that possible? He goes, well, they must be sport fishing. I'm commercial. I'm like, that's a thing? So yeah, firewall. We perceive of, analyze, and manage the resource completely different. And I'm like, whoa, out comes the tequila. And I could tell me, right? And so I get two things out of that night, a new stakeholder and the biggest hangover I've had in the last 2 or 3 years of my life. But it was interesting hearing how like I had no idea. I thought I had, that those were our stakeholders. Turns out I didn't, at least not until then. And what's interesting is that they told us, all of our stakeholders keep telling us, hey, look, back in 2006, we didn't know fish use the whole upper portions of the watershed. But we get that now, and we want to have a different conversation, which wasn't even part of the conversation back then. We want to talk about the groundwater, right? Here's that figure we've seen before, deep recharge, a couple of thin aquifers, water discharging to the stream. And they get it. They get that this, produces springs and seeps, which then support their streams. But they also get that these are pretty thin and low productive aquifers, and that when we put in houses, they drill down into those same aquifers. And as water comes out over here, it's diminished out here. So they're understanding now, okay, so this is a balancing act. There's a limited and shared resource between people who need it to drink and fish who need it for everything else. And the people are there, at least in part, because they want to value the fish. And so it's a very much a coupled system, and they want to have that conversation. They want to have a conversation about how to best manage their resources. And they just want me to be part of the conversation, not to tell them what I think, right? So the first thing they said was, well, okay, we got more of this happens, right? Like, well, that's 1,000 square miles. So I don't know, happens all over the place, right? I told you can't throw a pencil without landing in a wetland, or landing in a spring or sea. They said, no, it's not good enough. So we're currently now working on trying to figure out where this occurs. And we took a geospatial approach to it, right? So we have 6 watersheds. I'll go through some of these layers a little bit more detail here in a moment. We've got DEM and the whole thing, so we can create topo maps, and we can take DEM generated streams, and those are there. And flow weighted slope is a metric. I won't go into the details of it, but basically if you've got sort of a larger hill slope that's concentrating flow, so it can accumulate water, and it's steep, so it can drive the water, you get a high value. And the opposite, if you're on a convex slope, if you're flat, you can't either concentrate the water and or drive it. So in this case, red is a high flow weighted slope, yellow, not so much. Again, I'll come back to that in a moment. Topographic wetness index, you'll see it a little better here in a moment. Similar to the flow weighted slope, it tells us how water concentrates. So it'll show you where there's a hill slope that's concentrating water, or a stream that's concentrating water, or a big wetland that's concentrating water. And then the key, okay? So in the state of Alaska, anyone can drill a well. Don't have to tell anybody, ever. Pump it all you want, no rules. But if you want a state water right, you have to log your well logs. So if you guys have seen these before, they're formal pages that the driller fills out. And there's layer by layer information. Between 0 feet and 6 feet, it was silty sand. Between 6 and 13, it's sort of clayey sand, and so on and so forth. Well, he has to do this, right? Because somewhere down there's going to be a thin layer that's gravel and sand with water. And he's got to put down a casing that's solid except for that place where he can get sufficient quantity and quality of water that he can pump out. So these are very detailed. Now, most places like Montana, I bet you couldn't find them. California, where I got my PhD, no way. Zero chance of getting one of those unless you get a landowner to give it to you. State won't give it to you. State of Alaska makes those freely available. If you want a water right, you have to do this. They post them in PDFs. It's a laborious task for a grad student to go through 800 well logs and create sort of a point cloud or a point map of where these aquifers are. And then from there to sort of geologically model them, geospatially model them, and project them outwards to where they might intersect with a hill slope. And so we get a map of outcrops of aquifers that we know are filled with water and where they might express on the hill slope and be pouring some of that water forth. I know you don't see outcrops up here. That's because I don't have wells up there, right? Come back to that here in a minute. Suffice to say, we can use this now to help inform us about where these different kinds of discharge are occurring. So let's make that one go away for a moment, focus on the one on the left. This is that shallow groundwater at the hill slope scale, operating on the scale of days to months. Here's a place, there's a little stream, you can't really see sort of flowing down the middle of the valley here, but going through real quickly. Here's flow weighted slope. Remember, redder is higher, yellower is lower. Red means I've got a big hill slope that's focusing flow, that's steep and driving that shallow groundwater downwards. I can also project on here our DEM generated streams. And I could say then, hey, why don't we go right there? Let's go take a look. What are we going to find? I would say, hey, that's probably the place where groundwater discharge is occurring. And if I go to that spot, I find a hill slope covered with seeps. Okay, that worked out pretty well. And I can do this over and over again. It turns out these seeps are sort of only moderately productive. Those aquifer outcrops are the bigger springs. I really want to know where those are. So that's that one over here, right? So here's that muskeg, here's the deep recharge, here's the two thin aquifers and the discharge to the stream. I want to be able to find those springs. I'm going to do that a little differently. Give you an example. So that's a greenhouse. So that gives you an idea of the scale. And Twitter Creek comes right down here, flowing from your right to your left. Okay, so if I put down the topo, I can see some things here, these deep V-shaped valleys. Those are probably streams. Interesting, there's this little incipient drainage kind of thing. I wonder what that is. And if I do DEM generated streams, there's a little stream that goes up there. And if I turn on the TWI, here's that same stream. See how it gets kind of diffuse up here? Much more concentrated down here. Well, how about that aquifer outcrop? It's right there. It's right where it transitions from diffuse to more focused. And so I say, okay, well, how about we go to that spot right there? I bet you there's a big old spring there. And we walk to that point, and we're 41 feet away from that spring box. Okay, which I joke with the landowner. She's not in this picture. I joke with her that I just spent $500,000 finding a spring that she already tapped. But as just an example, we can find it doesn't have to be that one. So we got really good at this, right? I'm really good now at this. But again, this is it's 1,000 square miles almost. And here's the map of the land use land cover. Purple and sort of that lighter purple are well, the darker is native land, which I can't go on. The lighter is either state or municipal land. I could go on it if I could get to it, but notice that here's where the roads and the population centers are. Right? There's no roads up here. There's no way to get to it. So even though if I wanted to scan 1,000 square miles by hand, I would be having a hard time doing so. So what we're trying to do then is teach a computer to do it for us, right? That was the exercise here, and we're working on that using supervised classification to teach a computer to find these things that we can find so well ourselves. And then we'll go back this summer and ground truth it. Meanwhile, we're still having conversations with our stakeholders. Is this helping? What's next? Well, so what has happened, right? I've argued that if you just listen to people, and engage them, things will happen. That is a super low regulatory landscape. Like, remember that plot of warmth by competence? Feds are like at the origin in Alaska, right? Because they're from far away and they don't know about our wetlands and our streams. And they're jackbooted thugs who have bad intentions, and so they're not plotted there by Alaskan standards. But I would argue that probably are there. States hardly any better. I mean, the capital's in Juneau. You can only get there by airplane or boat. It's a long way from here. They don't know our systems either, right? Southeast is different than South Central. Tony's laughing. He worked in Southeast for a long time, and they're real different places. But the borough, what I call the equivalent of the county here, those people are competent because they live here. They know our systems. They're our neighbors. They're also interested in sharing the resource. They're one of us, right? So the borough said, hey, I got an idea. Why don't we convene a group of aggregate miners, big business, right? You can't make money selling aggregate if you have to drive it too far, so you got to dig it all locally down there on the Kenai Peninsula. So you got all these aggregate miners. So let's get all the aggregate miners. Let's get the resource and regulatory people. Let's get the scientists. Let's get some private people. Let's just get a group together, have a conversation. One of our team ends up on that group, and they themselves come up with their own ideas. Again, these are the miners themselves, and they say, hey, here's some things we can live with that we think will help. And so just last year, 3 groundwater-related updates to the ordinances were passed, one requiring 4-foot vertical separation between any excavation and the seasonal high water table, another one requiring 200-foot setbacks from aquatic resources, including springs. And then there was this interesting one, this big catch-all. If anybody can show that by impacting groundwater, there's been an impact to fish and wildlife habitats, that gets pulled in too. But it's voluntary, right? These are the miners themselves saying, yeah, this is a good idea. That's the last one that's regulatory though. Everything else is non-regulatory, either public or private. So here's an example. Here I said stream flow about 50% groundwater, at least started as groundwater. Well, okay, that means that the only place they drink surface water is the city of Homer, down on the southern tip of the peninsula. They've got a reservoir here. And I just went over there and sampled it and confirmed it's about 50% groundwater. And so I tell the city, and they're like, what? We thought that was all like snowmelt runoff. I go, no, it's like half of it spent its life underground. And they said, well, that's interesting. We'd like to practice source water protection, but we can't afford to buy the whole watershed, nor do we want to. Those are our neighbors. But all those people up there aren't on city water. They're on groundwater. So we see a potential conflict. Can you tell us where the springs are located? So now we're like, yeah, maybe, I don't know, go through that whole process. You see a whole bunch of stream looking things. So if we turn on our PEM generated streams, look how they all start at about the same elevation. It just seems like all over the place. If I turn on my topographic wetness index, I could see the same thing. Well, I bet you where we're gonna see this is in the aquifer outcrop layer, right? So now we're using this to predict where we think springs are located. So we can go back as part of our ground truthing in the summer and maybe tell them, hey guys, it looks like there's a whole bunch of springs right here and so on and so forth. Those are the places maybe you should purchase. Maybe we can do some scenarios modeling to look at how close a well could be, and a municipal or a household well could be without impacting the flows from those springs. And maybe you can sort of figure out which parcels you want to purchase versus which ones you want to just let be. Another non-regulatory public is this program with the Natural Resources Conservation Service. They will build you this thing called the High Tunnel. It's a big farm to fork movement in South Central Alaska. If you want to do that though, you got to abide by a few rules. One of which is you got to have your well logged and put it in the database. You also have to get your well water tested. You also have to practice wise water use. This is all drip irrigation, and engage in this conversation about why you might do that. Related to that, related to that is this. So they publish a landowner guide, which has, like I said, information on it. This is why we do this. Salmon are kind of cool and they're complicated, and there's some things you got to be thinking about. And here to explore your watersheds, and we've got a couple drone videos that help explain what they're seeing. And then there's this whole thing about researching your watershed where they can learn about our work and also engage us or figure out how to engage us. Related to this, Homer Soil and Water Conservation District. Oh no, wait, I'm not there yet. Now, this is actually more interesting. So this is the Cook Inlet keepers. They're usually the ones stopping development. They're the ones that fought Chewitna mine, and they fought, the Pebble mine. But here they have this voluntary program, farming in our salmon landscape. And again, it's related to this idea, this pressure to go farm to fork. And why that's a good idea, but why that creates conflicts that maybe we should resolve in advance. And so, there's all kinds of information here on there. This is one of their flyers about why this, because this is the largest growing farming district in the nation, and yada, 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 so on and so forth. And what they'll do is come out and work with the farmers to help them with things like water conservation to limit their withdrawals. And they'll explain why. And again, it's their neighbors. Like, they all know these people. They're not outsiders. So we also partner with some other non-regulatory private groups. So this is the the North Pacific Fisheries Association. And then these are our partners here, KBN and ours, Catchment Bay National Estuary Research Reserve, and the Kenai Heritage Land Trust. And we held these series of workshops called Fish Need Land Too. So here's these people that had this organization. They spent their entire adult life harvesting a marine resource at sea. And we take them instead to the headwaters, the furthest headwaters we could take them to. And we take them there and we put some fish traps in the ground and we pull out some juvenile salmonid. So this is a guy named Malcolm Milne. He's the president of the North Pacific Fisheries Association. He's beaming as he's holding this little aquarium because he's never seen one before. Or if he's seen one, he didn't know. A lot of these guys are like, it never even occurred to me. It never even occurred to me that this resource started in the headwaters. I knew they spawned and stuff, but it's never really resonated. Well, the interesting thing was after the series of workshops, the NPFA purchased a big chunk of this upper watershed position, donated it to the Kenai Heritage Land Trust for management in perpetuity, sort of saying publicly, we're a part of this. We want to be a part of this effort. And we're going to put our money where our mouth is. So that's this generation. I was sitting around thinking about what's going to happen next. And in fact, Jeff and I were talking like how long am I going to do this? And there'll be a time when I don't. And I was wondering, like, is this generation's thing? Is the next generation going to remember it? So this is last fall. I'm sitting around, and I've been working up there now for almost 15 years. I feel like I'm an honorary member of Homer. I feel like I'm an honorary member of the community. Still an outsider, but I'm interested. So I'm on all their list servers. So I get this thing, hey, the community council meeting is on Thursday or whatever. Hope to see you there. Well, I'm 6,000 miles away. Probably not. But I'm interested. Like, what are their topics? So I open it up, and I'm pleased that between 12:10 and 12:50 are the groundwater presentations by the Homer Middle School 8th grade class. I have nothing to do with this. Zero. None of us do. That's something that got organized somehow virally out of the work that we do. So I kind of feel like maybe this has taken hold and maybe it gets passed on to the next generation. I've probably talked too long, so let me just wrap it up really quickly. Obviously, I gave you the talk. This is not only my work. I'm just a small part of it. All kinds of people here that I can't possibly thank, and that's probably just a fraction of them. There, you'll see Bill, for example. Sort of acknowledge my funding sources. Big one here, and I hate to out it because I don't want to compete with you guys, but NOAA has the Science Collaborative program, which is about 1/3 science, 2/3 outreach. A super fun source of funding. So we just had $500,000 from these guys that just wrapped up, but also Fish and Game, EPA, and all kinds of partners, Smithsonian, Baylor, Catchment Bay National Estuary Research Reserve, which is a subsidiary of the University of Alaska, and all kinds of other partners that I can't possibly find and name. So I'll leave it here. This is some of the papers that I cited in this. I expect you to be able to write them, but just so you know, I guess this is getting posted. If you ever wanted to look more in depth at some of those things I passed through quickly, you can go to those papers and look them up yourselves. And with that, I'll take your questions. Nani?
So isn't Siri a big native corporation player on the Kenai Peninsula?
So the native corporation that we deal with on the lower Kenai is the Ninilchik. And they are mostly interested in the land of many uses kind of concept, right? So fish is a thing to them, but that's a small thing because this isn't like the Kenai River. You're not getting massive tourists on a lot of these rivers, a little bit, but they're more interested. They do some logging, bark beetles, putting a stop to that maybe, but there's a ton of oil and gas here, right? And so most of their land, so I said I can't go on most of their land because it's mostly oil and gas leases or proposed oil and gas leases, or they're doing seismic, so they don't want me to get blown up or whatever. There's all kinds of reasons they might not want me to do that.
I guess I was asking, have you tried to partner with those folks?
We did, and they used to be good partners, but something happened, and I don't know. So this is like a great example of stakeholdering, right? There was a stakeholder mismanagement there, and one day we showed up at one of the gates that we used to go through routinely, and it had a pole across it locked, a bunch of cameras, and a bunch of stay the hell out signs. And being me, I was like, well, I don't think they mean me. But then I got scared and I turned around and found out that, yeah, something happened over this last year, and we don't know quite what it is. So we've been sort of standoffish for the last 2 years or so. But they used to be a real active partner. They had a bunch of sites on their land. Some of the data I showed you was from their land, but it's sort of a mixed bag. There's also the Russians, right? So for you guys who don't know, there's these Russian communities there, these separatists that left Russia and set up shop in the United States. And they're very insular. They dress like Russians, they speak Russian, and they don't obey any laws in the United States. They're just like, we're Russians, stay out. They send their kids to school, and they're the best hockey players. They're also giant and vicious. But everybody just leaves them alone, right? So there's all their land too, which is sort of like you can go on, but they give you a lot of funny looks, and maybe you get some hostilities. So there's a bunch of this that's sort of weird, that where but it would be no different here, right? You'd have plenty of people around here you wouldn't want to go on their land, right? So it's just part of the engagement process. Sometimes it works, sometimes it doesn't. Chet, or so.
I have a question. So I've been part of a multidisciplinary team that's been looking at various ways of having the greatest efficacy in communicating science as it comes to hazard preparedness. And I liked your graph where it had competence on the X, and I can't remember what was on the Y. Warm. I was going to say warm fuzzies. Was probably
basically, it's the same word.
Right, right. And then recently this paper came out, and I find that to be, I have found that to be true in my experiences working in rural places, that, my place in the graph makes sense there. And this paper came out last year that randomized climate messages and attributed them to different sources. So whether they were attributed to Democrats, Republicans, military, or scientists. And it turns out that people download and will make decisions where they have there's greater efficacy when it comes from the military and from Republicans. And I look at that graph and I can't say that I put Rush Limbaugh like up in the like warm fuzzy or highly competent area. And yet, the science is really showing that these sources have a great effect. And so I've been struggling with my own conceptual model, like from my personal experiences and some of the science that we've been doing, but then also these other papers that have been coming out. And I just sort of wanted to get your thoughts on what does your conceptual model look like? How it works in this world?
So that's a really good point, and I didn't really get into that, but we've been thinking a lot about that exact issue. That there's a lot of source of misinformation, right? And you have to be seen as competent and as warm as that source of misinformation. And you have to be able to penetrate that market, right? I mean, a lot of those people are getting their information, say, from YouTube videos. So you guys would know this, right? There's some pretty awesome YouTube channels telling you how the government's lying to you and Yellowstone's gonna blow up and we're all gonna die and they won't tell us all about it, right? I don't know if you guys know any of these. Anybody know these? They're super fascinating. And if you look, their hits are like astronomical. Like it's got to be bots too, because like I can't believe there's literally 60 billion hits, but there's a lot of them because there's a lot of engagement in the commenting. And if you go to say the Yellowstone Volcanic Observatory, the YVO social media page, they're super excited to get 500 likes on the Facebook post, right? And so and that's Mike Pollock. I don't know if you guys know Mike. So Mike Pollock is just a regular guy like you and me, decided to become the social media expert. He doesn't even have a Facebook account, like he knows nothing about it. And he's sort of been slowly trying to penetrate into that market. That's the first hard part. How do you even get your information to that marketplace? Well, the only way we figured out how to do it, I told you my conceptual model, you go. Like I spent 34 days there last summer, and I spent a lot of those days, you know, talking to one person. Bill and I just wanted to go to this spring that we thought we had picked, and we got to go see if it's there. We're convinced we got to go, but so we're sneaking by this house. Maybe we should stop here. I'll go in the door. It seems kind of sketchy. Out comes this massive guy, and he talks to us for like 4 hours. All about why I used to ride bicycles up here. Now the road didn't sink, and we had to do this thing. Blah, 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 blah. You know, way back then, we used to smoke pot and go to Mexico, and blah, 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 and it goes on and on and on and on and on. But we learned a ton. There's all this other spring. There's a spring here. I'll show you right where it is, and you can have water at my well, and it, you know, becomes this long, engaged thing. Half a day, easy. Our co-PI and my wife, Kai, was not there that day. A little irritated that all we managed to do was 2 things in a whole day. To explain to her, like, no, it was super fun. But then when we came back, we're like, okay, the car's right there. We literally gotta we gotta go. Like, we're not even taking off our wet, muddy clothes. Like, get by them real quick. Hey, thanks, man. So, but that's it, right? It's we found that just going and knocking on doors, scary as it is sometimes, gets us in to where we can have that conversation, because otherwise, like, they don't read my papers, right? And I don't have a YouTube channel. If I did, they wouldn't watch it. I'm sure I wouldn't be as good at it. I wouldn't tell them the volcano's gonna explode, which is awesome, right? I wouldn't tell them they're gonna die. So you gotta find a way in the other way.
So we are after 1, so we're gonna have to, there's a class that needs to get in here
Okay.
now. Sorry, guys.
I can talk to him, and I can talk to you on the outside.
We're having beers at Columbo's at 4.